Welcome back. I have to apologize. I cheated you guys. In the last video, I forgot to do this bottom part here. I added this as an afterthought to my notes because I realized that this exercise 4 was kind of easy. There really wasn't much to it. And so I didn't really give you a good example of a function in terms of g of y. So I did another one down here. It's not in my notes. I just made it up for you. And then I forgot to show you how to do it. So I'm going to start off with that right now. Just go through the steps real quickly. So again, we're finding arc length. So here's my original function, x in terms of y. Taking the derivative of it, we get 12 square root of y. Squaring it, we get 144y. We have our bounds of integration, 0 and 1, so we put all of that together into our integral. Once again, we have to do a U substitution. So, U substitution, we have U is equal to 144y. Again, that's the integrand. The derivative of that is 144 dy, and dy is du over 144. And then, of course, I converted my bounds of integration from 0, 1 to 1 and 45. So plugging in, doing the U substitution right here, we have 1 over 44 times the integral from 0 to 1 of u to the 1/2 du. The antiderivative of u to the 1/2 is u to the 3/2 times 2/3, and I already did a lot of the simplifying because I didn't have a whole lot of room. And so we end up with, again, I told you you were going to see this a bunch of times, u to the 3/2. And when you substitute in, we end up with this. And once again, if you want to, you can play around with Desmos. Put this integral into Desmos, and you will get a decimal number. Convert this into a decimal number, and hopefully they will be equal. If they're not, then you did something wrong. All right, so now let's move on into area of a surface of revolution. So we're starting off with a curve, like we always do, some function. Now, in a previous lesson, we would revolve or rotate that function around an axis, such as the x-axis, and we found the volume of the object that was created by rotating. So that was finding volume by revolution. Well, we don't want to find volume now. We want to find surface area. Surface area is the total area of the outer layer of the object. It's the surface of the object. Could be completely hollow inside. We're just looking for the surface area. And so this has a very complicated development, and I skipped a lot of the steps. But basically, we do the same thing that we do every time we're developing some kind of an idea that involves, integration. So this basically is just showing you what we're doing. We're taking this function and we're rotating it around the x-axis, and we're getting some type of a solid object, and we're just finding the surface area of that object. So as always, what we're doing down here is we are breaking that function into some small line segments. Exact same thing that we did when we were looking at arc length. But this time, instead of just finding the length of these little arcs in here, we are rotating them around the x-axis. And we're finding the surface area created by rotating each one of these little line segments around the x-axis, creating some type of a solid object. What is the surface area? And so that gives us this right here, where each one of these little shaded areas is formed from a different line segment that was rotated around the x-axis. If you can kind of visualize that. Something like that. And so because these are line segments, we could use the slicing method of finding volumes that we learned way back at the beginning of section, I think it was 2.2. And we could find the volume of each one of these little slabs Now that's a little slab. Find the surface area of each one of these little slabs. And then we could add up all of those surface areas. And so that's basically what we're going to do. And so as I said, I skipped a bunch of steps. So once again, we're going to use a little bit of algebra, the mean value theorem from Calc 1, and we're going to end up with this representing the surface area of one of those line segments being rotated or revolved around the x-axis. Okay, and if you have to think about it, if you take one of these things and you cut it open, you take one of these, you rotate it around, you get something that looks like this, you cut it open, you're going to have something that looks kind of like a trapezoid. And so what we're doing is we're just finding the surface area of that right there. And so this formula will do that for us. So it is the surface area is 2 times pi times the function value f of x times delta x, and times, this should look familiar, yes, our arc length formula, okay? And our arc length formula comes into play here because that's what we're doing. We're taking these, arc lengths and we're rotating them around the x-axis. So you kind of figure that that's going to come into play here somewhere. So the square root of 1 plus f prime of x squared. All right, so that is the formula for finding the surface area of one of these, all right, one of these trapezoidal shaped objects. And then we want to sum up a whole bunch of those because we've got a whole bunch of these things in here. And so we're going to sum them up by creating a Riemann sum, and that approximates the surface area. And then, of course, as always, the next step is to let the number of little arcs lengths approach infinity. We take the limit as n approaches infinity of this Riemann sum, and we end up with an integral. And so the integral is the integral from a to b of 2 pi f of x times square root of 1 plus f prime of x squared. Now this is if it's being rotated around the x-axis. And so that gives us this formula right here in the box. If we were rotating it around the y-axis, then we go to that formula down there. Same exact formula, except that c and d are bounds on the y-axis. You have g of y here and g prime of y here. So that's your function x is equal to some function of y, rather than y is equal to some function of x. Other than that, the formulas are the same. So let's do an example. So again, be methodical as you're going through and doing these. I, again, like to start off the same way. I write down my function. I find its derivative, and I square it. Then I plug it into my formula, and I end up with this. This is what you would put into Desmos if you wanted to find a numerical value. So remember what the formula says. Let me zoom up to the formula. The formula, right here, is the integral from a to b. Well, we got that from 1 to 4. 2 pi, f of x. There's my f of x. And then we have our arc length formula, 1 plus the 1 over 4x. Now, what's tricky about this is the 1 over 4x. That takes some thinking about how you want to simplify that. So I did that over on the side. I actually did it on scratch paper first. And so here's what we did. Here's what we're starting with. Get common denominators. Well, 1 is 4x over 4x. So adding the numerators, we get 4x plus 1 over 4x. Now, this is the interesting part. You have an x down here in the denominator. Well, that x is underneath the radical sign. So technically speaking, you could write the numerator, I'm doing it over here, and the denominator in their own radicals. And if you really wanted to, you could write the denominator as radical 4 radical x. So what we're doing is we're removing that, all right? Taking the square root of x and removing it out here. And so if you think about it, if you multiply 1 over the square root of x times the square root of 4x plus 1 plus 4, you will get this. So all we're doing is we're factoring out the square root of x. Who would have thought? So now the radicand underneath the radical sign, 4x plus 1 divided by 4, simplifies to x plus 1/4. And so we have the 1 plus the square root of x. All right, so what do we do with all of that? So we put that over here. Rewrite what we had. Let's go to blue. So we rewrote like this. And now it's time for some U substitution. Again, let U be equal to what's underneath the radical sign. U is equal to x plus 1/4. Du is equal to dx. And so we substitute in, where did I do that? Oh yeah, and can't forget to mention that these cancel out before I move on. Those two just go away. So it simplifies to this. Now I'm doing my U substitution. I change my bounds to U bounds, plugging everything in. We end up with this. And so that's pretty easy to integrate. And we end up with surface area is approximately 30.84. This would be the answer probably in WebAssign, simplified algebraic answer. And as always, you could check your answer since this decimal equivalent answer with Desmos. All right, so they're very similar. The procedure is very similar to that of finding arc length. It's just that the formula is slightly more complicated because you've got this stuff out here, the 2 pi f of x. Other than that, it's just like the arc length formula. All right, shall we do another one? So now we have the function the cube root of 3x. So, as I always do, start over here with my function. Oh, yeah, we want to generate this around the y-axis. All right, so we're doing it in the y-axis, so I'm changing to x is equal to a function of g. All right, so that's what I'm doing over here. So y is equal to cube root of 3x. Cubing both sides, we get y cubed is equal to 3x, or x is equal to 1/3 y cubed. So that's my function. X is a function of y. Taking the derivative, we get y squared. Squaring it, we have y to the 4th. And so plugging all of that in, so right here, of course, we have our function g of y. G of y. Don't make the mistake of plugging this function in there, okay? Because the formula says that here we're plugging it, if we're doing it over the y-axis, that this has to be g of y, and that's g of y. All right, so just to remind you of that. And so, so I take pretty much the 2 pi divided by 3, bring it out front. That just leaves the y cubed here and a 1 plus y to the fourth. We can do that by U substitution. So u is equal to 1 plus y to the fourth. Whoops. Du is 4y cubed. dy is equal to du over 4y cubed. So plugging that in over here, substituting in du equals over 4y cubed, u to the 1/2. Now notice that the y cubed and the y cubes cancel out, so that's working out very nicely. And so we end up with just this. And now we can find the antiderivative of u to the 1/2 is u to the 3/2 times 2/3 times the pi over 6. And we end up with this algebraic answer and this as a numerical answer. And just in case you're wondering where the pi over 6 came from, you're probably looking and go, where did that pi over 6 come from? I was wondering the same thing myself. Pi over 6 comes from the 2 pi over 3 and that little 4 down there, all right? Okay, so you end up with 2 pi in the numerator and a 3 times 4 in the denominator. So that cancels there and you end up with pi over 6. Don't forget your constants in here. Next. So we got 2 more. I'm just doing 2 videos tonight, I guess. All right, so f of x is equal to x cubed. And we're looking at the portion of the curve from 0 to 3. And we're going over the x-axis. So pretty straightforward. Again, your function, the derivative squared. Plug that into your formula. So you have 2 pi f of x and your radical. And so this is going to be a U substitution. One indication whenever you're doing an integration problem and you wonder whether you can use U substitution or not, generally U substitution is going to work out when what you would be using for your U. So if I'm using this as my U, the power is 4, and you have an x out here that is 1 degree less. That's usually going to mean, I can probably use U substitution. Let's see if it works. So over here, U is equal to 1 plus 9x to the 4th. Du is 36x cubed dx. Dx is du divided by 36x cubed. And I changed my U bounds here. Plugging all that in. There. The x cubes cancel out. That 36 goes underneath that 2 pi and simplifies to pi over 18. And then u to the 1/2 is u to the 3/2 times 2/3. Evaluated from 730 to 1. And so our simplified algebraic answer is right here. And our numerical answer is right here. And check that with Desmos. All right, so all of these problems in this section are fairly routine as long as the integration doesn't get too tricky. And pretty much U substitution is about the only integration technique we can use right now because we don't know any other techniques yet. I think the next problem, no, not this one. It's in another set of notes. All right, so 1/4 x squared minus 1/2 log of x. Consider the portion of the curve from 1 to 4. And we want to revolve it around the x-axis. That's not sure what that was supposed to say, but we're doing it around the x-axis. So over here, I did some algebra. There's my original function. Here is the derivative of the function. Remember, the derivative of the log of x is 1 over x. So the derivative of 1/2 log of x is 1/2 times 1 over x, or 1 over 2x. That's where that comes from. Well, we want to get common denominators here, clean that up. So 1/2 x is the same as x over 2 minus 1 over 2x. Common denominator is going to be 2x. So I got my common denominators of 2x. I have to change that numerator. And then actually subtracting the two fractions, we get x squared minus 1 over 2x. And then squaring that, you've got to square the binomial in the numerator, and you've got to square 2x. And so we end up with this. That looks ugly, and it is. And so now we plug that into our formula to get that. How are you going to integrate that? Well, this is another one of those where you got to play around with the fractions. So that's what I do. Whoa, down here. So let me explain what I did there. First of all, I get rid of that. So first of all, this is my starting point. Get common denominators. So 1 is 4x squared over 4x squared. Add the numerators together. Now, 4x squared is a perfect square. So I can simply take the square root of that and remove it and put it out front. So it's 1 over 2x. The square root of 4x squared is 2x, so we have 1 over 2x times this. And it just so happens that that is a perfect trinomial square. Yes, sirree. X squared plus 1 times x squared plus 1 is equal to that. And of course, we write that as x squared plus 1, quantity squared. And so we are now taking the square root and squaring that, and we end up with this, which is a little bit nicer to work with. So we have x squared plus 1. We'll see how I work with that up above, over 2x essentially. Yep. And so take that and write that here. X squared plus 1 over 2x. And so this x cancels with this x. This 2 cancels with that 2. So we're left with pi integrating from 1 to 4 of x squared plus 1 dx. So that's pretty easy to integrate. We get 1/3 x cubed plus x from 1 to 4. And so here's my algebraic answer. And that is simplified algebraic answer. I don't have a numeric answer. And I think that was the last one. Got a whole blank page in there. I could do an extra problem if you want. All right, so these take a little bit of practice. But again, as you go through and observe how I'm doing these problems, there is a certain pattern, a certain style of how you should go about doing these. Just like with the volume problems, just like with any type of a problem, kind of get your habit of doing a certain procedure, a certain way. All right. Hope you enjoyed it. See you in the next video.